No, I will get back again. Now differential. Now differential, basically differential maps one vector tangent vector to other tangent vector in the image manifold from M to N. Now what I was talking about, the submanifold. Yeah, submanifold using F. He talks about Sard's theorem as well, which I was not at all able to understand, and I don't find its importance as well. Sard's theorem. Now we will come to the idea of submanifold. Basically, submanifold is you have a manifold, and if you can somehow give some of the coordinates differentiably in terms of other remaining coordinates, you get a submanifold. Basically, you have on a M N, you have on a patch U x1, x2, xn, and what so happens that up to xk you take these points, and the remaining point xk plus 1 up to xn can be given differentiable in terms of other, that is xk plus 1 in terms of function k plus 1 x1 xk and remaining for xn. And these points x1 x these functions what is the dimension of this manifold? Now these functions will form a manifold of what will they form? What dimension manifold? What dimension of submanifold will they form? Let me think. We have R2, and then we more form S1. Let's take R3 is 2. There are k plus 1 relations. Yeah, they form a manifold of k dimension, the number of independent variables. So yeah, this is some idea of some manifold. In the starting of the chapter, he discusses it with respect by taking M as an Rn, and then discuss submanifolds. Is that all? I think, yeah, that's all. Now the theorem of submanifold using differential. So we have a function f from M to N, and yeah, you can do a little bit here using implicit function theorem. Basically it says that, I don't even remember these functions. If you can give some these functions in terms of all other, you give some, I will leave it because I don't even remember that. No, submanifold using differentials, yes. So submanifold using differential, is basically a theorem which states, so it is useful because in the starting point, the starting section, in the half section, before the half section, he uses it to prove that for a rotating body, yeah, the points on the rotating body lives in a submanifold of R3. Yeah, that's it. That's it. Because configuration space of a rigid body lives in R9, but configuration space of a rotating body lies in some manifold of dimension 3, and it's O3, SO3 in fact. So that I will just state the theorem that this is the theorem. S1 on 2. Yeah, I think that's, I don't remember, but basically it says that if you take F inverse y, yeah, and it's not empty. If it's empty, then we can't do anything. But if it's not empty, then we can do a little bit here. And if the differential at a point, the differential at that point, which links f inverse y, is onto, let's say x is onto, then we can say one thing, that f inverse y forms a submanifold of Fn. That's what it says. Yeah, this is the theorem. He doesn't give any example, and afterwards after this section he talks about Sart's theorem. I don't find any special use about it. It's a bit complicated. In fact, it talks about measures and stuff. And the last thing is integral curve. I didn't get the last section about straightening the flows, but before it basically says that it's basically it's about existence and uniqueness of differential equation. No, I don't even remember it, so I will upload it. I will talk about it in the next video after reviewing it. So this is what I remember. Wow, come on. I'm amazed myself. I remember so less even after reading it twice. So yeah, that's it.